Hey everyone. So today I want to talk about system design for FP live comments. So what that means is, let's say a video is being live streamed, and then the users can comment on that particular video. The users should be able to see the video's comments, and they should be able to scroll up if they want to look at what other comments were posted by other users who are viewing this video at the same time. So we will refine the requirements of this design as we move forward, as we progress in this particular video. But that's the intention of that's the goal of this particular video. Now, before I move forward, I want to have one disclaimer, which is that a lot of what I would be talking about today is inspired by two particular resources. One is by Hello Interview, and the, the article goes on like this one. There's no corresponding video for this particular system design, but that exactly is the resource through which I've learned a lot of things about how to design FB Live comments system. The other thing is a video by someone by the name Akhilesh Gupta. There's a video which he there's a seminar which he presented at InfoQ in 2020, and just this one, how to stream million likes per second. So yeah, these two particular resources are what are driving today's system, and that's it. Now, with the disclaimer done, let's start with the actual system design. Now, before we move forward, while moving forward, we need to talk about what exactly are going to be the functional requirements of the system, and there would be few. So one, use post a comment. That is the first thing. Second is let's say kind of live stream or watch the comments, watch or view the comments in real time, as in like whatever other users are posting, be able to view them at the same time in real time. Third is go back into comment history. So for example, view the comments which were posted before someone joins the video, the live stream. So view older comments. Now there are obviously going to be some out of scope requirements, which are, the first is like reply to a comment itself. We are not going to support that. And yeah, these are the few functional requirements that we have. Then there are some non-functional requirements. The first is high availability. Over consistency. What that means is that the system should be available even if a comment which was posted by any user around the world, he or she would be anywhere and he is watching the same video. If they make a comment, I'm okay with waiting for a couple of seconds or whatever, but the system should be available. So there will be eventual consistency, but availability is more important. So eventual consistency. Okay. Then we would be talking about high scale. So this is going to be a Facebook scale, and though I'm not going to define what exactly the scale would look like at this point in time, we'll come to that later. But that is another non-functional requirement. Third is so we have scale, we have high availability, and the third, yeah, these two are non-functional requirements. And here as well, we have some out of scope requirements. So the first is that something like talking about the sanctity, the properness of the comments, as in like people should not be abusing each other, or typing in foul language. That should not be supported. That should be supported, but we are not going to solve for that in this particular design. So out of scope is proper language. The other would be, let's say, kind of a CI/CD pipeline or some kind of a monitoring system. Monitoring in this kind of system is required in the case like we will obviously work towards high availability, which would mean some kind of fault tolerance. But there would be invariably there would be some failures, and we would want to understand in the future what exactly caused that particular failure. So that is why monitoring is important, but we are not going to have a monitoring systems design in this particular system design. So these are our functional, non-functional requirements. Now let's talk about the core entities, and I'm not going to go into detail of these core entities as of now, not required, so as to speak. In the current situation, we'll cover them as and when the need comes. So there would be four core entities, I think. So first would be comments, obviously. What exactly are we going to comment upon? What is the content? Second is where are you going to comment this? So there would be a video. Third would be who is going to comment this? There would be a user. And yeah, I think that's it. Yeah. Let's talk about APIs as well. What exactly our APIs would look like. And these APIs could change. So there's two caveats here. One, these APIs could change. So just what I'm going to suggest here is more of a broader picture, so as to speak. The other thing which I want to talk about is that the users are authenticated. That's the assumption. Assumption users are all authenticated. And the other thing is that authentication information is retrieved from JWT tokens or user tokens. There is no other way. I mean, we are not going to pass user ID in the payload. That is a security risk for the APIs. There will be again two APIs. One we have is our post request on the comment. What exactly the comment would look like, and this will have a video ID. Rather, the parameters will look something like this. We have a video ID, which will be something like this, and then we'll have a comment section, which will be some kind of text. This will be posting, and then the other would be a get request for fetching the comments. So this will be again comment, and this will have some parameters. We will come to them later, but let us keep it as a placeholder here. And with this, all the preliminary work we need to get started with is done, and we can move on to the actual design part of this particular video. So let's get started. Let's talk about that. There is a user machine or user browser, user client rather. It's not necessarily that user will be using a browser. They could be using a app as well, and then they'll talk to a load balancer. AWS, let's talk about AWS API gateway. This will be doing a couple of things. It will be load balancing, there would be routing, there would be rate limiting. By the way, routing and load balancing are kind of similar. There would be authentication, so I will just remove routing for now. After this, we will have a client write service. We are talking first about writing or posting a comment. So comment write service is, let's short form for CWS. And what happens is a user makes a request where they want to post a comment with the video ID. And this post request is routed to, oh, by the way, routing is different, my bad, let me add it. Yeah, okay. So there would be a call here, post comments. This will write to a database. Now the question is what kind of database this is. This is your comment database. The question is like, Would this be a SQL database? Would this be a non-SQL database? And comment DB. And for what it's worth, a lot of advancements has happened in the past few years, where the functionality, the abilities of both the type of documents, though the type of databases have merged. What you want to get done with a SQL database could be done with NoSQL database as well, unless and until there are some specific requirements. Now, in our particular case, we do not need we do not have a lot of intertable relations, and that is the most obvious reason why you would use a SQL database. The other reason I would go for NoSQL Dynamo database is because it is automatically managed by AWS. A lot of headache is taken care of by AWS, though there's a vendor lock-in kind of such a scenario, but still we do not have to think about how it's going to scale. And given that we are trying to design something like scalability, design something like a FB kind of system, it has to be able to scale enormously. So instead of going for self-managed document DB like Cassandra or whatever, where we'll have to invest some engineering mind power in managing them in the DevOps part of it, so as to speak, we are just going to use Dynamo database for this one. So that's the first thing. Now the second thing is, what exactly is going to be the table, the entity going to look like. So there will be a comment table for sure. There will be a comment ID. Then this would be there would be a video ID, which would be FK, which would be a reference to some other FK would be used in relational terms. There would be video ID, there would be a user ID, and then there would be a timestamp kind of a thing. Now the question is, what exactly is my primary key? What are my secondary keys? Wisdom says that your video ID should be your primary key because it will help you fetch the comments for a particular video, and then you can use either user ID or timestamp for the sort key. For sort key, timestamp makes more sense, but I'm going to use user ID for that. And the reason is that I need timestamp for first of all local secondary index, and the reason I'm not going to use timestamp for local user ID, sort key, is that there could be situations where two people sitting at different places, watching the same video at the same time, could make a comment. Now, if you use timestamp as a sort key, there might be a case of conflict, and yes, there would be there might be difference in milliseconds, but they cannot be as well. So we do not need to do that. We do not need to fall for that kind of situation. If we have user ID as a secondary key, that kind of scenario will not arise, because one user will not be typing comments on the same particular video from two different devices, even if in some weird case the same user logged in two different machines and two different clients, and they are watching the same video. Even then, the probability of hitting a comment at the same timestamp is next to, I don't know, it's very, very low. So that's why we are going to use user ID as a sort key, and then timestamp will be our local secondary index, which will help us sort the comments of that particular video. So that is one. Then we'll have two more tables, which I'm not going to go in detail, but they are video, which will obviously have a VID column, then it will have a user ID column, and then there will be the metadata. Similarly, we'll have a user table, which will have user ID and then some other metadata. This would be age, gender, ethnicity, and so on and so forth. So cool, this is our Dynamo comment database, where this particular database, this service writes are coming to. Okay, so the first functional requirement is done. User is able to post a comment now. Now comes the second part, where the user wants to retrieve comments from this particular video. So the user will make another API call, which will be get, and get slash comment slash again VID. So we are passing a video ID here. And then there would be a comment read service, comment read service, which will be like, okay, I want to fetch comments, and then this will read from this particular database. So far so good, but the question is how we are going to read comments in real time. Now the first, so for this particular requirement, let's write down the different options we have. So fetch comments in real time. Okay. Now there are a couple of approaches. One is that we can polling, and what this means is that every client will make request at a periodic basis to our comment read service, which will then make a request to our comment database. So these arrows have to be double-sided, and I forgot to while defining the APIs, I forgot to talk about the response type. Just give me a minute and I'll come back to that. Okay, so before, just take a pause here. So the response type of this one would be 200 OK. So the status code, and hopefully it is always 200 OK. The response to this might be, let's say, a comment object, depending upon how you're going to think about the query, how you are going to structure the API, and that's what we are talking about right now. So I'll just leave this here for a while. Now we were talking about polling. So the polling will be doing regular periodic requests to our API gateway, which will in turn make the request to read service and DynamoDB. The problem with this approach is that this fails at a scale. Even if there's, if you are doing any kind of multiple requests, we have to do two things. One, we'll have to horizontally scale our comment read service, which is possible. And of course, the other part is also possible where you read a lot of data from the Dynamo database. The problem here is that because there would be a lot of reads, you're going to incur a lot of cost. So user A and user B who are polling every 1 second, and they might be polling synchronously. Still, because there are different requests, you will have to read the data from the database again, duplication. And the solution could be that, why not just have a cache, but let's hold that thought for a while. So polling will not work. The other thing is that we need to have constant some kind of understanding of what exactly was the last comment. So in the sense that if my last comment, last read was at 5 seconds, then the next read should come, or the next set of comments, next tranche of comments should come just following that. And that would mean some kind of state mechanism if we are going to use simple polling kind of a thing. So a better way is having a direct line of communication, a persistent open communication connection between the server and the client, and then the server can send the data without the client asking for it. There are two kinds of solutions for this. One is your WebSockets, and WebSockets is a good solution here. The problem with WebSockets though is that WebSockets is good for a situation where the communication is both ways. For example, a gaming situation where I am constantly updating the location of my avatar, and I am also constantly fetching the location of different avatars, like something in Counter-Strike or Dota or Call of Duty. So that is one thing. The other thing is that that is one example. The other example could be a chat application where I am constantly pushing messages and I am also constantly receiving messages from the server. In our particular use case, we do not want to do that. Yes, we have a situation where we can make a comment, but we already have a post request for that, post out for that, and it's not happening regularly. If I am posting a comment, let's say in 1 second, I am receiving comments. I might be receiving comments 200 in 1 second, and it is not necessary that I will be posting comments in every second. I might be posting once a minute but receiving 60 times a minute. So WebSockets is not necessarily ideal for that. So WebSocket is generally used in cases where bi-directional communication is required. Equal read write balance. The other thing is that it is a different protocol than HTTP, and which means a lot of maintenance. So more maintenance, different protocol than HTTP. Okay. So that is why WebSockets is a good solution but not a great solution. And the third solution which we are going to use is server-side events. Now what are server-side events? So again, this is a bidirectional bidirectional persistent connection between the source and between the client and the server. The difference is that this is only for the server to send messages, to send data to the client. It is not the other way around. So it is a bit, and the other thing about server-side events is that it runs on HTTP protocol itself. You just have to pass a different header while sending a request, which is /livestream, and then you have to implement event source at the backend. But it's comparatively straightforward. So that's why you're going to use server-side events. So again, persistent connection between client and server runs on HTTPS. Okay, so this is our choice. Okay, and now our servers can send constant stream of messages, constant stream of comments to our user. This satisfies our second requirement as well, where how will I see the messages in real time. So this takes care of that. Now the third question, which is that I should be able to what is it? I should be able to view older comments. Now again, they are, apologies for that. So when we're talking about view old comments, there are, I think, a couple of approaches we can think about. So one, we can just use pagination, and there are two types of pagination, at least two types of pagination. One is your offset pagination, which is provide the offset and size of the response. The problem with this approach is that the offset will change. Right now I am talking about the offset 3. So in offset you divide the comments or divide the data into different tranches, and then you can define, okay, I want the first tranche, I want the second tranche, I want the third tranche, and the definition of tranches happens by just basic calculation. It's not that you've defined and that definition remains persistent. It changes over time. So offset pagination might work for situations where the write is not happening very frequently, or write happens sporadically. But in our case, write is happening very fast. So I make a comment right now, I make a request right now, and by the time my request reaches the client, reaches the server, it is possible that there are 200 extra comments in the span of milliseconds. So the offset will change. That is problem number one. Problem number two is what happens if we delete a particular comment in between. So pagination works, offset pagination works, but it's not the best solution out there. The other type of pagination which we can do is a cursor pagination, where we tell the backend, the server, that hey, give me 15 comments, 20 comments, whatever the size of comments, before this particular comment ID, and that is what we'll be doing in this particular case. So the request will look like request will look like, it will be a get request on slash comments, and the parameters will look like, of course it will not look like this, it will look like slash comments question mark vid equals to abc, and we have offset equals to cid, which is comment id, ampersand limit equals to, or size, other size equal to, it could be 10, it could be 20, or whatever you want to keep it. So this way we can make sure that our pagination works pretty well. We can fetch the older comments. So the third question comes about is speed. How can we speed this up? Now there is one solution where we can kind of pre-fetch the comments. We can do before the user even reaches a place where they are going to make a request. We can make a request and store data in cache somewhere in the cloud. The problem with that approach is that the first problem is not many users are going to, or rather very less fraction of users are going to view these older comments in real time. Most of the users would be just looking at the comments, posting comments in real time. Very less users would want to look into the history of the comments when during the live feed. However, there are cases where the users might want to look at the comments when the live stream has happened and it's a previous video that they are looking into. So in that situation, we can think about having a Redis kind of a thing. But again, that would be very limited. One user in one particular geographical location is looking into the comments for this particular video, and is scrolling through all the comments. So normal API requests are not too lengthy as well. There might be some delay, but you don't need to necessarily cache the data unless you are really obsessive about it, which is in some particular product situations it's good. So pagination with caching is a third approach, which in my case depends upon a balance between the cost that you're going to incur and the importance of that particular product feature, and it would require some kind of discussion with the product team. So pagination with caching and pre-fetching case-based situation. So this takes care of our third functional requirement as well. Now we are good, and we can start talking about the non-functional requirements. So high availability over consistency, this is to be configured. We do not need to talk about this in detail, but the question is how we are going to scale the system. What if we have an FB scale of, let's say, so the most common, the most viewed rather live stream was of around 180 million views in parallel, which means that we have to give data, we have to provide comments in real time to around 180 million users, which is huge. So even with WebSockets, we need to figure out how we are going to do this. The first solution is, so let me talk about scale now. Okay, scale is 180 million views, parallel views simultaneously. Okay, so this is our problem statement. Now the question is how we are going to do this. So the first solution is horizontal scaling, and now the question is how we are going to serve our machine. And by the way, this is for one video, not for other videos which are being streamed in parallel. Live streamed. Anyway, so now horizontal scaling is one thing, but how does my server know which comments, which videos I should be comments of which video should I be you know sending. So what I'm trying to say is that even if we do horizontal scaling, I want to figure out how are we going to, or rather which comments of which videos I'm going to give back to the user through a server-side event. So for that we can use a purpose system. Okay, what that means that I will subscribe to some of the videos which so what will have is let's draw a bit. Okay, what is going to happen is I will have a client here. Okay, there will be n number of clients. So let's just assume that this is scaled. There are more than one clients. Okay, and then they talk to your comment read service. CRS. Okay. Now the question is, how does CRS know which videos are to be, which comments from which videos are to be given back to the clients? So the most obvious thing is that it can keep a mapping of the different users watching different videos, and then it can subscribe to those particular. It can just send those particular. What I'm trying to say here is that it is subscribing to all the videos, and it is sending messages, sending comments of only those videos which are being watched by the users. So the mapping would look something like this. You have a VID, and then you have a list of users. You have user 1, you have user 2, you have user 3, and then you have VID1, sorry. You have VID2, which is user, let's say 4, only user 4 is watching this, and then you have VID3, which is being watched by user 5, user 6, user 7, user 8, and so on and so forth. Okay, and then the comment database, the Dynamo comment database. This is which has this has n number of videos. So let's assume that for now we have v1 to vn. Obviously n could be anything. So what happens is and then there is a so this is your CRS. Well, the way it can work is this: you have a CRS here, and then you have your comment writing service here, and then you have your different publishers. And these are horizontally scaled, so maybe I should have drawn them differently. I will just okay. So okay, now this particular service writes to this. This is producer, and then this is your consumer. Okay, now this talks to this, and this is a two-way communication. Okay, so first of all, this would be a one-way communication, so I'm going to remove that, and this again would be a one-way communication. Okay, so first of all, this is your website. This can work. The problem with this particular situation, and of course this writes to this as well. Okay, and these will writing here as well. So this closes, completes the picture. The problem with this approach is that this is a bit, rather not bit, this is very unoptimized. Now my CRS has to subscribe to all the 100 videos, even though the users which are subscribed, which are connected with this particular machine, are looking at only 3 videos. So there's a 97 video redundancy here, which we do not want, by the way. This is a different kind of redundancy. So horizontal scaling with PubSub is not a great solution. The other solution is horizontal scaling with partition PubSub. What that means? We have PubSub subscribe to specific topics. Okay. What that means is, let me just copy this complete thing here and make it other. Sorry, that is point number 1. I just these, and I have these. Okay. Now, my particular so there are different topics now. Let me now remove this thing. Okay, apologies for being silent for a while I was writing. So what I'm trying to do here is that now we have a PubSub which is partition within topics, and topics could be one topic for each video, and also depending upon what exactly is the hot shot kind of a thing. So there would be cases where one particular video is very hot, the 180 million view wala thing. So then you'll have to do a division of that particular hot shot as well, but we'll come to that in a while. Or rather, it is covered in some other videos. I'm not going to talk about it. What exactly is happening here is this, that you have different in the PubSub system, you have different topics, and then different instances, horizontal instances are subscribing to different partitions, different topics. So that way, now this machine does not need to subscribe to the other 97 videos, other n-3 videos, which the users connected to this particular service are not talking to. So this solves that problem, but if you look closely, it solves only, I mean, the problem can resurface. What happens if users like user 4, multiple users join this particular system and they are connected to this particular device itself? In that particular case, we will have a situation where my CRS is attached to or subscribed to a lot of topics to which there is only one particular client, and that is again a suboptimal kind of situation. And it can happen because the way we are going to assign, the way we are going to route the users to the different machines is in a round robin fashion. So probability anything can happen. The third way to avoid that kind of solution, that kind of situation, is using a V7 load balancer. So for this, we do not need drawing this kind of situation. So I'm just going to add here use V7 load balancer with PubSub subscribed to specific topics. Now the good thing about a V7 parallelly, okay, anyway, so the way a V7 load balancer works is it routes different requests to a specific server. So what happens is, let's say a user who wants to watch video ID 2 wants to connect, which is, let's say, user ID 10 wants to connect, then it will route that particular user to that machine where users watching that video are already available. So in that sense, it makes sure that it is not subscribing to a lot of topics. And the way this is configured is by a message in the header. So whenever I'm sending a request, I will obviously send which particular video I want to connect to, and then the load balancer will route that particular traffic to a specific machine which already has users connected to this particular video. Now the caveat here is that in these situations that particular machine could become too hot. There could be a lot of users assigned to that particular machine, and the health might deteriorate. There might end up being a single point of failure. So for that reason, we want to make sure that we have configured P7 load balancers properly. We have a proper auto scaling of properties in place. So that kind of configuration is important, which makes the solution a bit trickier, but it works. So this is the great solution which we have. The other solution, before moving to the another good solution, which finds a little mention in Hello Interview, but finds a great deal of mention in the other another video by Mr. Gupta, is about using a dispatcher service, which I'll come to in a while. But before moving forward to that, I want to talk about what exactly this subsystem look like. It could be a Redis thing, a Redis cluster, or it could also be something like Kafka. Now Kafka is great. Kafka has inbuilt fault tolerant system. It has redundancy in place. The problem with Kafka, and I'm going to quote Hello Interview here again, is that it does not work very well with situations where there are a lot of connections and disconnections. What I'm trying to say is that right now a user is looking at video 1. He or she might very quickly change to video 5, and then they might again very quickly change to video 7, and this might a very random process, so to speak. And it has been told that Kafka doesn't work great in that case, so that's why we are going to use Redis, which is what I'm going to update here now. Now the problem with Redis though is that you'll have to think about managing all these issues which Kafka gives you out of the box. For example, redundancy, for example, fault tolerance, and you'll have to think about these situations. You can configure multiple Redis cluster. You can add some redundancy in there. There's a situation where the data might get lost because it has been written so fast. By the way, that doesn't happen in Kafka again. So these kind of situations you have to take care of when using Redis, but because they can be handled in Redis, but the other way it cannot be handled in Kafka. That's why we are not going with Kafka. Okay, so this is also done. Now, the fourth solution is using a dispatcher service, and I'm again just going to write it here. What that means is, let me maybe try to draw it here. What that means is there will be three kind of machines. One, there would be a client. So let's talk about, sorry. So we have, let's talk about for dispatcher service. And the way it will work is that we'll have, let's say, n number of clients. So I'm just going to draw one client for other clients, and then there would be a front end node which sends messages again through SSE to these different clients. So let's say message nodes SSE, right? And these contain a mapping of which particular client is watching which particular video. Okay, mapping of client to video. Okay, now this particular guy, this particular machine talks to another service, which is your dispatch service. And the mapping this particular node has is between message node to your, not the client, it has the video. Okay, so that is the difference. So whenever a new message comes, it comes to a dispatch service. The dispatch service dispatches that particular request, or it sends the request through SSE, to our message nodes, and it will obviously send the relevant message only to those message nodes which are serving that particular video. So it is possible that there are overall 5 videos being are running in parallel, and my machine 1, which is, let's say, this one, is subscribing to only 2 videos. So this dispatch service will send, depending upon this particular mapping, send only the comments for those 2 videos to this particular machine, and then in turn this particular machine can send the comments selectively to the clients which are subscribed to video 1 or video 2. Similarly, we'll have the scaling. So there will be another machine which is subscribed to, let's say, 3 videos, and another which is subscribed to again 2 videos, so on and so forth. This particular machine will work. So it is some kind of this system. And this is the system through which LinkedIn live comments work. There's also a great solution, no problem with that. There's no pop-up system here, it's just dispatch. There were a couple of challenges here. One was how do you fan out? I mean, you have to figure out what exactly is the ideal machine size for defining number of machines, not machine size, the number of machines for a load, something like your again, quoting examples from that video, a royal wedding or the live match between India and New Zealand, semi-final, anything. So that is through trial and error, but yeah, so that is what wraps up our system design for FB live comments. And fun fact is that I recorded this video an hour or 2 back, in fact around 2 to 3 hours back, but for some stupid mistake I ended up recording the wrong screen. So that video had just audio, but all the screen, all this drawing which I am doing here was not recorded, and that's why I am recreating this video. So I think overall my performance has been better as compared to the video which I recorded earlier, rather the audio which I recorded earlier. Anyway, so yeah, that wraps up our system design for Facebook live comments. Thanks for watching. Thank you. Bye.